Hi guys, welcome to the data structure implementations with JavaScript. Before we get started, I feel an obligation to issue a disclaimer and state that I'm only a beginner with data structure and algorithms. In fact, I've sucked at it for a long time. I've only recently gotten a little hang of it, but there's still miles to go. That said, while I relearn what I try to teach along this process, I'd recommend that if you're a beginner to an intermediate level programmer, irrespective of your choice of language, practice algorithms and data structures as much as you can. Every other push-up does in fact add to your strength, even if you don't just see it. Okay, let's get into it without wasting any more time. The prerequisites that you would need to follow along this video is a basic understanding of JavaScript. You'd need Node.js installed, you'd need Visual Studio Code or any other IDE of your choice, basic understanding of object-oriented programming, and if you want to refer to the MDN docs for JavaScript with object-oriented programming, this is where you get started. And as always, I'll leave all the links down in the description for easy reference, and then you could check them out. So the top 5 data structures in terms of usage and their must-know ratings, in my opinion, are arrays, linked lists, stacks, queues, and trees. Let's maximize this. Now, obviously, there's graph and heap and seemingly unending variations. I just decided to leave them out since you could understand them just fine once you knew these 5 well enough and would usually get by with using just the basic ones. Again, just an opinion. So let's start with arrays and then work our way through the other ones. Now we know that everything that we define in JavaScript is an object, and so is an array API. To test that out, let's try to do this. Define an array and then console log it so that we see the type of the variable that we've just defined. So let's do that. Press run. By the way, if you don't see this little play button here or you don't see the run code option here, it means that you don't have the code runner extension installed. To get it, you want to go to the extensions tab here and then type in code runner. It is the extension by Jun Han. It's really popular and has the capability to run way too many languages. And I cannot stress on how awesome this is because you get the ability to debug your code and then run it right in the IDE itself. So I really recommend that you get it. And now back to the code. Let's get this panel to the right so that it's easily readable. And notice that the type of the variable that we had defined as an array is an object. So basically what an array is just an object with numerical keys and a length property that's managed automatically for you. And the array API has a bunch of other functions such as push, pop, reverse, and a bunch of other ones such as size and so on and so forth. Now, if you want to check the documentation, you'll find all the functions there. But in this case, we're pretending to recreate an array API. Consider this. If we were to define an array with a bunch of values in them, it can also be represented in the form of an object like so. Internally, what's happening is the array object that we have here is indexed with numericals such as 0, 1, and 2. I understand that it's a little weird to have an object with numerical keys since that's literally what an array is for, but it paints a good picture that arrays are just fancy objects. Let's test that out. You have to save it first. Right, there you go. So the actual arrays element at the first index and the object where we pass a key as the first index both print 1. Since we're trying to simulate the functioning of an array, let's use the prototype object to do it. Now, if you don't know what a prototype object is, it's a property that every JavaScript object has and provides the mechanism by which JavaScript objects inherit features from one another. Well, with that in mind, we can take the first step to creating our very own arrays. So let's get rid of that. And we know that an array will have a prototype object and there'll be a length property which delegates to it. So let's define that. Let's do it with a function array. And let's define a variable array equals to object dot create and then array dot prototype. Now that's just a syntax. And then we'll delegate the length property to it and initialize it to 0 and finally return the variable. Now the benefit to using the prototype object is that we in effect route all field lookups to array.prototype. We may now add all the methods we want and it will be shared across all the instances to it. However, before we do that, we need to add indexes to the values in our array. To do this, we'll make use of the argument object, which is an array-like object accessible inside of functions that contains the values of the arguments passed to that function. If that's a little fuzzy, it'll get better when we see it's working. Let's go ahead and use the for in loop to loop over the arguments and add the keys and values to our array and increment the length. So we'll begin with for key in arguments. This can be anything. Sorry, that's terrible. Now this can be anything, say X or whatever you want to call it. But if you keep it intuitive, it's better. It's going to be array of key. So the index would be equal to arguments of the key. And then we'll also need to increment the length by 1. And that's it. We are now ready to add all the methods to our array function. And since we want all the methods to be shared across all the instances of the array, we'll be putting them on the array.prototype. So the 3 methods that we will be implementing are these. So we'll do push, pop, and filter, which is basically the standard method of any given array function. Let's start with the push function. Since we're using functions, we need to figure out which instance invokes the method that we're trying to define. And here is where we'll use this keyword, which will reference the instance which called it. To test it out, let's just say a console log this, and then call this function. Let's say we have an array called best with these values in them, and then let's just call that function. And consider that these are the arguments that are being passed to this function, which would be substituted in the place of arguments, and the prototype object takes care of the function that are delegated to it. Let's run this. And there we go, we get all the values with the indexes appended to it. Let's get rid of this. A function adds an element to an array, right? So how do we implement this? Let's begin by placing the element at the index which would equal the length of the current array object, variable best in our case. So we'll do this and this dot length, which would be the index. This here, this refers to the variable that we have, and this dot length would be the length property for that particular object. And we'll place the element here and increment the length and return it. That's it. If you were wondering what exactly are we trying to push to this array here, congratulations, you're thinking right. Don't be disheartened even if that did not occur to you. Each in their own time. I know I still take mine. So anyway, we need to pass something to push in the form of an argument here. So let's say, for example, we push in, I don't know, Marlin. Well, these are table tennis players. If you're wondering and don't know about it, just happen to play a little bit myself. Anyway, so we do this and we will accept a variable in the form of element here. So let's test this out. Well, we don't see anything happening because we haven't logged anything here. So if we go ahead and do a console log, we will see that the length would be returned. So try that, and we have the new length, that is 4, which with this element being appended to this array here. Also, just to make sure, we could also do a console log and print the whole array itself, just to be sure. There you go. And as we had defined it, it has all the values with the indexes and the length property. Likewise, in the pop function, we'll have to reduce the length and delete the last element. So let's begin with this dot length and reducing it by 1. And then let's define an element to discard. Let's call it discard, or let's call it discard element. And it has to be camel case. And this element would be this, which will refer to the object that would be calling it, and the length of that object would be the index. So this is the element that we want to delete. Remember, that was the element that we were trying to add when we were doing push, and now while we do pop, we want to discard that element. We could use delete that element start length, and then finally return the element that we have discarded, or you can return the index or whatever, whatever you want to return. And similarly, if let's say we do best.pop, we don't have to return anything here. And let's see. All right, there you go. We have deleted Marlin, and and that was the last one, if you remember from the one that we had before. And to make sure, we could do a console log of the whole array and check it out. All right, there we go. So the last one, Marlin, value has been popped. Let's move on to the filter method. This is a higher order array function among others. To name a few, we have for each, map, and reduce. What a filter method does is that it creates a new array with elements that pass a specific validation, and we can specify that validation in the form of a callback. Let's specify that there. And to create it, we'll loop through the given array and use the callback function to make the check and push over whatever matches into the new array. To begin with, let's do result equals a new instance of an array object, and let's loop the current given array, and then this time we'll loop through the index. So we'll do let index in the current instance of the object. Then we need to define an element which we will be pushing to the new array. So we'll do const element equals this of index, and we also will need to check if the element exists. So we'll do if this dot has own property. The has own property function will take an argument index. We'll put that inside, and then we need to make sure that this function checks the validation of the callback function. So we'll do callback, and that will take the element argument along with the index, and whatever the result would be, provided that the callback returns a true value, it will push the element into the new array. And then finally, outside the for loop, we will return the final result, which would be the new array. Now let's see if this function works. Test this. What we'll do next is best.filter, and then this would take a callback, and here is where we would set that validation. Let's say person is an arrow function, and it will return person dot, let's just do char at for now, so that let's keep it easy. The first letter of every element will be checked, and just to keep it easier, we know that there's going to be m and m, so at least two values there. So we'll do m and see if this would return it. Let's go ahead and run this. Okay, it says that caret is not a function, but I know that it is. Now this looks like it should work, but although the error log is not very accurate, I know that the caret is in fact a function. In the constructor of the array function that we've defined here, we have used a for in loop. Now by default, what it would do is it would loop over all the enumerable properties of the object. What we've also done here is array.length, and in this case, this is also an enumerable property. So what we will do here is use another function by the name of define property. It is not very common, but if we alter the constructor of the array function or the core logic by object.define property, we'll be able to allow ourselves to add a property on an object and specify if that property should be enumerable or not. So let's do array and length and we don't want this property to be enumerable. So it would take another argument in which we would set the value to 0 and the enumerable flag would be set to false. And then we could set the writeable flag as well to true, since we should be able to change it. And I think that should be it. And then we'll also console log this whole thing so that we see what is being returned at the end. Let's also remove these console logs here so that there's no confusion in the log that we see, and comment this out, and now try to run it. Okay, this was supposed to work the other way around. Oh, I see. So what I've done is I've added the check to be not equal to m, so that behavior was expected. These two values, malin and malong, are being omitted, and the other values are just being filtered out and then being printed in the array. So there you have it. That's the array API simulation, or a simple array implementation. We could obviously add in as many functions as we want, but I just wanted to cover the basic ones right now. Let's move on to the linked list. Let's tidy this up a little bit. Clear out the console and create a new file. So we'll be doing a linked list implementation. Simply put, a linked list is a chain of nodes implemented by each node having a link to the next. We use pointers to get a reference and thus traverse through it. The head points to the first node and the last points to null. To implement this, we'll define its structure and then a few methods that we would want our linked list to have. Let's begin with defining a node, and we'll use the class to do it. Let's do class node, and it'll take a constructor with some data, and this dot data would be equal to data, and we'll have another property next which will equal to null for now. So that's the basic structure of a single node. And let's create another class, say linked list, and add another constructor which will define its head. Again, it should be this dot head, and this will be null at the beginning. We now have the basic template ready, and we'll go ahead and add the functions that we want in our linked list class. So the functions in a linked list class, for example, would be print. There'll be insert, let's say size, to the linked list, that is delete the whole thing. And we could probably make variations with the insert by adding it to the end, to the beginning, or in the middle. So let's do insert after, insert to the end, and then insert at the start. I guess this is good. Let's implement these functions here. Let's begin with the insert end function. This function would add a node to the end, which would mean the last node in the linked list will point to another node, and then the newly added node would then point to null. So the function will take an argument data, and we will use the node class and create a new variable. This will be a new node which will take that data. So the structure that we have up here, the new data will be added to the data, and then the temporary next pointer will point to null. So the first thing we'll check if the head is null, and if it is null, we will point the head to the node that we've just created. If that's not the case, then let temp equals head, because we don't want to change the position of the head. And as long as there exists a next property in temp, which is head right now, we will loop it. So let's do while temp dot next is not null. We need to traverse the linked list, so we'll do temp equals temp dot next, and then when it reaches the end, we will place the node that we've created in the place of temp dot next, which would at the moment point to null. That should be it. And also we won't be able to test it out unless we print it, so let's complete the print function as well. We can choose to print it in multiple ways, but the easiest that I find to do it is to push the data from every other node into an array and then print out the array. So let's do that. Let's begin by copying the head. So let's do node equals this dot head. Let's also create an empty array. And what we want to do is, while the node that we've created exists, we want to traverse that until we find the last value and then push the data from every node into the result array. So we'll do while node and then result.push node.data, and then do node equals node.next to move along the linked list. And of course we'll have to return the result array. Well, that should be it. Now that we have these both functions up, let's create an instance of this class and then push some values in. Let's begin with creating an object. We'll name it LL. New class name, linked list. And let's insert a few values in it. Insert end. I'm just adding in random values here. And then finally, let's do print so that we can see what's happening in there. Let's run this. We've just returned a result here, so we'll have to console log it. And we should be able to see the values now. Right, there we go. Let's now do the function to insert a node at the beginning of the linked list. This one will take a parameter, data, and we'll begin by creating a node. So let's do let node equals new node of data. We'll then point that node to the current head. So we'll do node.next equals head. And then finally, let's change the head to point to the node so that the start remains the same with head pointing to the linked list. I'll do head equals node. That's it. Say for example, if you want to do insert start 8, and then let's try to print this. We see that this is inserted here. Now let's move on to insert after. I intend to create this function to accept a couple of arguments, a node after which we want to insert a new node and the data of that new node. So let's do previous and data. I'm just calling previous the node after which we want to insert our new node. However, you could make variations to it and maybe accept an index or a position to insert it at. As always, we'll begin with creating a node with the data and check if the list is empty. So if head equals null, we need to place the node at the head. So head equals node. Else, what we want to do is point the next property of the node that we are trying to insert to the previous node or the node after which we are inserting something, and then point the next of the previous node to the one we've inserted. So node.next would point to previous.next, and the previous node's next property will point to the current node. Let's also test this. In this case, we'll have to use a couple of arguments. So let's just do ll.head.next to get the second node in the linked list, and then data that we're trying to insert can be anything, so some random value. Let's test this out. Right, there we go. We have inserted 45 as well. Now the important part is done, and the remaining two functions are fairly straightforward. Let's start with the size function. What this function would basically do is traverse through the array and count the number of nodes it has and return it. Let's begin with defining a node which will point to the head, and declare a count variable which will be 0 at the beginning. And to traverse the list, we'll do a while loop. While node exists, we'll increment the count and move the pointer ahead. So node will equal to node.next. Finally, return the count. And the clear function is the easiest that we have. Basically, what we do is just kill the head. we'll go ahead and set the head to null. And there we have it. That's the whole linked list implementation. And the final step is to just test this out. We'll do ll.clear, then print it. And also let's print out the size here. Alright, that's everything. Alright, there we have it. Initially the linked list has all of these data that we've pushed to the array and printed it out in the print function. The size as is printed here is 7 from this array. Although the size here is not the array size, it is the linked list size because we're traversing through that list. And finally we're clearing the linked list here, which returns an empty array when we print it out at the end. Let's move on to the other one. Let's do a stack implementation now. Let's create a new file. Clear out the console, start afresh. A stack is a linear data structure which follows a particular order in which the operations are performed. Now it's easy to remember if you think of its working mechanism of the order last in first out or first in last out. In other words, it only has one point of entry and exit for the data that's coming in or going out. It usually has functions such as push, pop, and peek. So let's get to it. Let's begin with creating the class stack. And within its constructor, we will have the data as usual. And this will be an empty array at the beginning. And it will have another property called top. This basically is just the length of the array and is usually called top because the de facto is to visualize the stack as a vertical array, and it will be initialized to 0 at the beginning. Let's also define the other functions within this class itself. So that we'll have push, peek, pop is empty. Let's also do a print function. Let's add in a function to get the length, and let's also do a reverse function. I think this is enough. The push function will take an argument. Let's call it element, and we will be placing this element at the top of the array data. So this dot data, and we'll place this at the position which will be equal to this dot top element, and then we'll have to increment the top. So this is basically the length of the data array, and the index is top here because it has to be at the last position. The peek function is basically to see what data is at the last position, and since we are visualizing it vertically, top is a pretty appropriate term here. So what we'll do here is just return the topmost element with this dot data, and the index would be this dot top -1 since we need to return the data in the last position. Let's do is empty before we do the other ones. We'll check if the top is null or 0 in this case. The length similarly is pretty straightforward too. We just need to return this dot top. Let's move on to pop. The first thing we'll check if the stack is empty or not. So since we've already defined the isEmpty function, we'll make use of that. So we'll do if this dot is empty, if this is false, do this dot top equals this dot top -1, since we'll be decreasing one element from the array, and then return the data dot pop. Now I know that we are actually using a library function here, but we're just trying to understand the functionality or the mechanism of the data structure. So, you could go ahead and actually manually do it, but for the sake of understanding right now, let's just go with the library function here. For the print functions, we want to start with the top and decrement it until it is 0 and log the data at every other step. So let's do let top equals this dot top -1, and while it is greater than 0, we want to log it. So console.log this data of the top. and we'll have to reduce it by 1 in each iteration. And finally, for the reverse function, we will use recursion to do this. We'll create another function. We'll name it _reverse and pass in this dot top -1. When we define it, this will take an argument index. Since we want to go from the top to the bottom, we will start with top -1, which is the last element, and go all the way to 0. So the first check we'll do is if index is not 0, we will recursively call this function here and pass an index -1. Finally, we will also console.log it this dot data of index. That's it. Let's test this. We'll begin with creating an object of the class. So new stack, and initially let's just push a bunch of values in them. So then the first thing that we want to check is trying to print every single value. Now the print function here prints every value one by one, but if we choose to just go ahead and console log the object dot data property, it will just print out the whole array, which is basically the same data, only in different formats. So let's test both of those out. All right, there we go. We have all the single elements and the whole array all together. Now the reason that we see this top to bottom is that we conceptualize it as a vertical array. Let's test the other functions. Let's do a pop and then try to print this again. Comment this out, and we can see that 10 has been popped. If we want to do the is empty check, we will also have to console log this, since it only returns the boolean value. It prints false, which is expected. Let's try the reverse. If you notice this and compare it to this, you can see that the sequence has been reversed. Did we miss anything out? Oh, the peak function. Finally, let's start peak. We have returned it, I believe. Yeah, so we'll have to console log this. And the peak value is 34, I believe. So let's just comment out everything else just to be sure. Did I not save it? That was weird. But anyway, so this is the top value right now. I guess that's it. Let's do queues next. Clear out the console, new file. Much like a stack, a queue is also in effect an array, usually visualized horizontally with different data entry and exit points. This is generally used in a pipeline mechanism where you want to stage instructions or data to be executed in sequence. It follows a first in first out order. Since the queue is actually an array, we will use the functions from the array API. Let's begin with the class queue. In the constructor, we'll have to define an array. I'll call it elements, and this has to be this dot elements. The functions that this class would have would be enqueue, which is basically push. This will take an argument e. We will push to this dot elements. We'll be deleting an element from the queue, but we would be deleting an element from the start. So let's do this dot elements dot shift. That will delete an element in the beginning. Revert could be another function which will take an argument e. So if you want to reverse the process of dequeue with the same element, if you have a mechanism to pass in the same element again, maybe from a cache or memoization or anything else, this is what you will use. we will take that argument and then do this dot elements dot unshift, and this will take the parameter. And we could use the same functions from the previous stack implementation, such as isEmpty, console log is dot elements dot length. It will print out the boolean and check if it is null or not. Peek could be another function here. This will just log the topmost element if the elements array is not empty. If not, this empty, so this dot elements of 0. And this here is a tertiary operator, just in case if you're wondering what the syntax is. Probably have to remove this console log and return the boolean so that I'll be able to use it here. Length could be another one, so you don't have to return it, you could just console log this dot elements dot length. As I said, we'll just be using the functions from the array API because that's basically what a queue does. You could do it manually, but the objective of this exercise is to understand the mechanism of how this data structure works. So you can leave that out for now. Print is probably the last function I can think of right now. So console log and then print the array. That's it. Let's test it out. Begin by creating an object, new queue. So pushing in a queue is called enqueue, and then let's add in a bunch of values, and then let's do queue.print to see if this works. Yeah, let's do queue.length, queue.isEmpty. We'll have to log this, queue.dequeue and queue.revert, and pass in, I don't know, if you have a caching mechanism you could pass that same value here, but right now we could just pass in something random to reverse the dequeue process. And then finally queue.peek to know the latest element in it. So let's test all of that out. And there we have it. So that's queue. And then finally, let's move on to the tree implementation. Let's clear this out. And we will be doing a binary search tree. A tree is a node-based data structure that intends to simulate a hierarchical tree structure with a root value and subtrees of its children with a parent node, represented as a set of linked nodes. A binary tree is a form of a tree which has a maximum of 2 child nodes for every node that it has. And a binary search tree is a variant that satisfies properties such as the left subtree of any given node contains nodes with values lesser than the node's value. The right ones are greater in their value. And finally, both left and right subtrees must also be binary search trees. Since every tree data structure is node based, we will start with a class. So I'll define that. And the constructor will take some data and will place that data into a data property. And this will have 2 properties. This dot left, which will initially be null, and this dot right, which will also be null. And let's create our BST class here, binary search tree. And then this will have a constructor as well, and the constructor will have a root property which will initially be null. Again, this should be this, and it will have functions such as insert, remove. And to print it out, we have 3 methods to do it. We could either print it in the pre-order sequence, in order sequence, and post-order sequence. We can also define a few other functions such as, say, find the minimum node. We could do get root, for example, and I think that should be enough. Let me actually define the objects that we would be using eventually. Assuming that all the functions are already set up, we will be doing bst.insert, and let's add in some random values. Let's also visualize all of this data in the form of a tree. This is how it is going to look like. Let's begin with the insert function. This will take an argument data which we are going to be inserting in the tree, and consider that these values are already in the tree, which we can visualize like this, and we are trying to insert a new data, say 40. So what we're aiming to do is this. When we try to insert the new data, which is 40 in this case, it will first be compared to the root, which is 100, and if it is less than the value here, it will go to the left, or if it is greater, it will go to the right, and then it would check the subsequent values and then go further down if it doesn't match. And if it comes across a null value, it will place itself at that particular position, and hence this is called the depth first approach. So let's implement that. We'll begin with defining a node. So where new node equals new of node. This node will take the data as an argument, and we will check if the tree is null. So the first thing we'll do is to check the root. This dot root. If this exists, we'll have to insert, and if it does not, we will just place it at the root. And for the logic part here, let's just create another function and recursively call it so that it makes it easier for the depth first approach. So let's create a function called insert node, and then this will take two arguments. The one would be the root and the other would be the new node that we've created there. Let's define that function now. The first argument would be a node, the root in this case, and the new node. Now we have to compare the new node's value with the current node and then traverse downwards. So let's begin doing that. If new node dot data is less than node's data, begin with the root. We'll have to go left, and when the data is larger, we'll have to go right. So the first thing to do in here would be to check if the node at the left position exists. So we'll do a null check there, and if it is null, we will place it at that position, and if that exists, we will make a recursive call, and then the new root would be node.left with the new node. Similarly, we'll have to do that for the right side. If node.right is null, let's place it there, and if it exists, then recursively call this function so that it will go to the depth and then find the null value and place the element that we're trying to insert. Node dot right and new node. That's the insert function, and then once we insert all of that, we'll have to print it. So the three methods to print are pre-order, in-order, and post-order. To begin with the pre-order one, let's do the node check. If it exists, we will console log it, and we'll log the data, and then recursively call the same function with the left node first, and then followed by the right one. So the print is pretty straightforward. For the in order, we will be printing the left side first, then the root, and then the right. So again, if node exists, we will make a call first in order, node dot left side, then console log the node's data, and then likewise the right side. Similarly for post order, it'll be 2 recursive calls and then the console log. So node.left first, then the right side should be post order, and then console log the data. That's all it is to printing it. The get root function is basically just to get the root. That's it. For finding the minimum node, we have to get the leftmost node in the tree. So the check that we need to do would be node.left. If this exists, we'll make a null check. We'll return the node if the left side of a particular node is a null value, or else if it exists, we will return a recursive call on the same function with the left side. Should be it. Before we move on to the remove function, let's test all of this out. So the first thing is that we've inserted all of that, and we won't be able to see it unless we print it. So let's do that. vst dot, let's print it in pre-order first. Node, oh my bad, all of these functions will take the node parameter because we need to start somewhere. We usually start with the root. So, and I also forgot to add in the check here. And that's better. And then we will have to pass the root here, and thankfully we have the get root function. So let's define a variable, say x equals vc dot get root, and then pass in that here. Now let's test it out. There we go, and the new node 40 has also been inserted, although everything follows the same logic. Now let's do the last function. I saved this for the end because this might take a little bit of effort to understand, so I want to try my best to explain what I'll be doing here. So here goes. When we delete some data or remove a node with that data from the binary search tree, we get a series of possible scenarios. We will handle them all through recursion and adjust the parent nodes all the way up to the root to get the final modified binary search tree. The remove function will accept an argument data. This is the data that we need to find in the tree and delete it. And deleting the data is going to ultimately modify the root. So we will change the root, and the value which will be returned to the root finally would be the result of the recursion of another function. So let's define one and pass in the root and the data. Let's call it a node and the key. The key is our data. The best case scenario is if the tree is empty, so we will check for a null value on the root itself, and if that is true, we'll return a null. Then there are 3 main possibilities. The first would be if the key is less than the data that we are looking for. The other possibility is if the key is greater than that data. And finally, when we actually find the actual data from the particular node. Now we have to traverse until we find it. So there are going to be two other recursive calls in both the left and the right part of the binary search tree, and when we actually do find it, there are going to be 4 possibilities here. So we will start marking them. Either that particular node would be a leaf node, which means the left is a null and the right side is also a null. The other possibility is if the left is null but the right exists, and right could be null and the left side exists, and finally there could be multiple child nodes. When we do find the data and when it's a leaf node, we will just mark the node as a null and then return the node. Now returning the node would go back to where the call was made from and readjust the parent node, and this happens all the way up until the root changes and the BST is adjusted. If we have a left, we'll do node equals node.right, then return the node. If right exists, we would mark it to left and then return it, and this needs to be else if. And finally, when there is a multi-level tree at one of the sides, we will replace the current node with another node with the least value on the right side. So let us define a right least value variable, and we'll actually call the find minimum function here and pass in the right part of the tree, and then we will do node.data equal to right least.data, and then on the right side we will make a recursive call and pass in the right and the right least data. And return the node. And in the previous two scenarios, when it is less, node.left will get a recursive call with the left side passed along with the key, and then return the node to adjust the parents. And similarly here we'll do node.right equals this dot remove node dot right and a key, and then return the node again. And that's it. Let's test it. bst.remove, and so you want to remove 40, and then print this again. It's a little hard to tell, but this is the first print, and this is the second print without the 40 in it. So there we have it. That is the BST implementation. I hope I did okay. This tutorial was by far the most daunting I've ever done. Algorithms and data structures have never really been very intuitive to me, and after years of struggling, I can finally say that I'm not afraid of it anymore. Although I still cannot always visualize the process and need constant clarification, or I have to go back to it a lot frequently than I would like to. But the major takeaway that I want you to have is to take a break when needed, any number of them, but always get back to it. Develop an attitude to dominate or go down swinging. I'll just leave you with that. Peace out.